You ever look at a recursive function and just wonder what it's really doing under the hood? In terms of performance, it can feel like a total black box. Well, today, we're going to crack open that box and demystify one of the most visual and honestly intuitive tools in all of algorithm analysis, the recursion tree method. So here's our game plan. We'll kick things off by talking about why analyzing recursion is tricky in the first place. Then we'll introduce our visual solution, and we're going to put it through its paces with two really different examples. And finally, we'll talk about where this method fits in your larger analyst toolkit. All right, first things first, let's really nail down the problem we're trying to solve. Before you can appreciate the solution, you've got to understand the challenge of actually measuring what a recursive function costs. I mean, this is the fundamental question, right? A function calls itself, which then calls itself, which calls itself again, and you get this long chain of operations that can feel like a tangled mess. So how in the world do we untangle all of that and just calculate the total work being done? Well, the good news is, instead of getting bogged down in abstract formulas, there's a really elegant way to visualize exactly what's happening, and that's where the recursion tree comes in. So what is this thing? The idea is actually incredibly simple, but so powerful. We take that recurrence relation, the math formula that describes the recursion, and we literally draw it out as a tree. Every node in that tree is the cost of a single call. Then all we have to do is add up the cost of each level, and then add up all the levels. It's that straightforward. Okay, theory is one thing, but this method really comes alive when you see it in action. This is where we're going to get into the details. And just a quick heads up, we're focused on building your intuition here. If you want to dive into all the nitty-gritty formal proofs, don't worry, I've linked all those notes in the description. For now, though, let's build a tree. All right, let's start with a real classic. T of n equals 2t of n over 2 plus n. So what is this thing actually telling us? It's saying that the time to solve a problem of size n is whatever it costs to solve two subproblems that are each half the size, plus some extra work, n, that you have to do to put the results together. If you've ever looked at merge sort, this pattern should feel very familiar. So let's start drawing. At the very top, at the roots, our cost is n. Simple enough. Then, at level 1, we split into two problems, and each costs n divided by 2. So the total work for this level? It's 2 times n over 2, which, hey, that's just n again. Okay, let's go one deeper. At level 2, we split again. Now we have 4 problems, each costing n over 4. Total work, 4 times n over 4. And what do you know? It's n again. Are you starting to see the pattern here? It's pretty cool. And that's the big aha moment that the tree gives us. The amount of work isn't shrinking as we go down the levels. It's not growing either. It's perfectly balanced. Every single level of this tree costs exactly n. So now, calculating the total cost becomes almost trivial. It's just n plus n plus n over and over again. The only question left is, well, how many levels are there? And that's the final piece of our puzzle. How deep does this tree go? Well, at each step, we're cutting the problem in half. So we're really just asking, how many times can I divide n by 2 before I get down to 1? And that, my friends, is literally the definition of a logarithm. So the tree has log base 2 of n levels. All right, let's put it all together. We've got log n levels, and every single one of them costs n. You just multiply them together, the number of levels times the cost per level. And bam, you get theta of n log n. And the absolute best part is that we didn't just blindly apply a formula. We actually saw why that's the answer. Okay, you ready for another one? This next example looks almost identical to the last one, but you're about to see how one tiny, tiny change to the formula creates a completely different looking tree. So here's our new recurrence relation. T of n equals t of n over 2 plus n. Did you spot the difference? It's subtle, but it's crucial. That 2 in front of the t is gone. Now, instead of creating 2 subproblems, we're only creating 1 subproblem that's half the size, plus that same n amount of work. Let's draw this thing. The root, level 0, still costs n. But at the next level, we only have one branch going down to one subproblem, and its cost is n over 2. The level after that, just one branch again, costing n over 4. See how different this is? Unlike our balanced tree, this thing is shrinking, and it's shrinking fast. So when we go to add up the total cost, we get this series, n plus n over 2, plus n over 4, and so on. This is a classic geometric series. And you can see it with your own eyes, right? The cost is massively front-loaded. Almost all the work is happening right at the top. Now, here's a really cool property of a decreasing geometric series like this one. It converges. The sum will never ever exceed 2 times its starting value. So the total is always less than 2n. And you know how it goes with big theta notation? We drop the constant factors. So it's just theta of n. Look at that. We removed a single 2 from the formula, and the complexity just collapsed all the way from n log n down to linear time. That's the power of actually seeing the work. So, we've seen how powerful this visual method can be. But you might be thinking, hey, what about the master theorem I had to memorize? It's a fair question. So, how does the recursion tree fit into the broader analyst's toolkit? You know, I like to think of it like this. The master theorem, that's your power tool. It's super fast, but it only works for very specific kinds of recurrence relations. The substitution method is what you use when you already have a strong hunch about the answer, and you just need to formally prove it. But the recursion tree method, that's your discovery tool. That's for when you don't know the answer. It's how you build your intuition and actually find the pattern in the first place. And really, that's the main takeaway. The power of the recursion tree method is that it transforms abstract math into a concrete picture. It takes the complexity of an algorithm out of just formulas on a page and turns it into something you can actually see, explore, and most importantly, understand intuitively. So I'll leave you with this thought. Complexity isn't just some abstract concept. It has a shape, a pattern, that you can literally draw. So the next time you write a recursive function, I want you to stop for a second and just picture its tree. Is it wide and balanced? Is it tall and skinny? Is it shrinking? And what hidden inefficiencies can you find now that you know how to see them?